I will talk about Today I will talk about global spin alignment in relativistic heavy ion collisions. I will give a progress review. I will first discuss what are the global spin polarization and spin alignment, why they're interesting, and what we have learned from the study of global polarization and alignment so far. Then I will focus on the discussion of STAR's recent results on global spin alignment of phi and k star mesons. At the end, I will give a summary and outlook. We know that in non-central heavy ion collisions, you have two spectators passing by each other with a finite distance. That will produce large orbital angular momentum, and that momentum is deposited in the interaction region. And then the viscosity dissipates the vorticity to QTP fluid at a larger scale. This angular momentum, it can be transferred to spin degree of freedom of final state hadrons. This is proposed by Professor Zuotang Liang and Professor Xinian Wang in 2005. This is an interesting notion, interesting phenomenon, because the angular momentum is a notion from classical mechanics. The rotation is a concept in classical mechanics, and the spin is a notion in quantum mechanics. Usually, the classical world and quantum world, they do not interfere with each other, but through this phenomena, it has a connection. I haven't found out any other example that you can make such easy connection with. So with that, we have to mention two phenomena. One is Barnett effect, and the other is Einstein-de Haas effect. Those two effects are dual version of each other. The Barnett effect is that you can generalize magnetization through rotation. So you rotate a rigid body, you can change the spin of the atom or electrons inside this material, and that will produce a magnetization. The Einstein-de Haas effect is, on the contrary, if you produce a magnetic field, that will cause polarization of electrons. And that will change the angular momentum. To balance this change in angular momentum, because the angular momentum has to be conserved, then it will produce a rotation. So to me, what is more intriguing is this Barnett effect. Again, that's, as I said, you probably cannot find another example. Say, I can do some simple operation in everyday life. I just keep rotating something. I can change. I can influence the quantum mechanical world. I think to me I appreciate this phenomenon very much. This is amazing. If you talk to friends who is not doing physics, they probably would not believe you, right? But you can bring up this Barnett effect. Say, I can simply by rotation, I can influence the quantum mechanical world, which is you can change the spin. This Barnett effect and Einstein-de Haas effect is they continue to be an interesting topic. So people are studying, say, in spin hydrodynamic generation, they study the vorticity in the fluid and how they interfere with the external magnetic field. People are studying the Barnett effect in solids by nuclear magnetic resonance. And people also study Barnett effect in paramagnetic states. This is after a century since those effects been discovered. And at RHIC and RHIC, we can study such effect at extreme conditions. How do we do that? We can study that by looking at the Hyperon global polarization. The lambda, well, we mainly do that. We first did that by lambda. Well, that's the easier one to deal with, of course. Lambda hyperons are self-analyzing. That means the proton tends to be emitted along the spin direction of parent lambda. in practice, how you do that, you have here you have two colliding nuclei, you have a reaction plane, then you have this direction of the angular momentum, which is normal to the reaction plane. So what you did is in lambda rest frame, you look at the proton's direction, and then you measure the angle of that proton with respect to this L direction. That's the theta angle. Then you got a distribution, and you feed it by this equation. You can derive this pH denotes the lambda polarization. There's another alpha. That alpha is used to describe the intrinsic smearing between the proton momentum and the lambda spin direction. So that but that number is well measured. And you measure the lambda hyperon polarization, and then you can infer the polarization of quarks, because according to the flavor spin wave function, the polarization of the lambda hyperon is carried slowly by the strange quark S. This is the measurement. This is, of course, no news to you. It's on the Nature cover. The STAR experiment studied the lambda polarization as a function of energy, and it's extremely significant. The conclusion is that the fluid produced at the RHIC is the least viscous, and it is the most vortical. And this paper has a very significant impact. It's among the 1%, is top 1% in terms of citation with similar age or papers. Now, why we're interested in this quark global polarization? Because it has a connections to many other physics. For example, we know the hadronization will produce a quark global polarization. I said before that this local vorticity, it needs to dissipate into the whole system, and that means it has it is convoluted with hydrodynamics, and also also the viscosity has an effect. And because we're dealing with local vorticity, it can probe the vorticity field, and the vorticity field has a connection to another interesting effect, which is called a chiral-vortical effect. We know the classical magnetic field will also produce quark polarization. And recently, people also realize the same mechanism that produced the chiral-magnetic effect. That means you started with excess of local chiral charge, but this chiral is also related to the spin. So it also has a connection to the quark global polarization. That's the same phenomena which is responsible for a local priority violation. It can also produce this quark polarization. Then there's this strong force field, which I will talk about more later. So in a nutshell, we are interested in this study because this quark global polarization, it has an insight to rich physics. Then why we're interested in global spin alignment, given that we already know the lambda polarization? Here I have to start with the vorticity field. Because we know the vorticity field is all the function of the x and the pseudo rapidity. And that means when you study the lambda polarization, because the lambda polarization is related to the vorticity field, it cancels each other when taking the average. And this cancellation is even severe at high energy when the odd function becomes more smooth. But there's no such cancellation for global spin alignment. So that's one reason we studied global spin alignment. There are other reasons, but first, let's introduce what is vector mass and global spin alignment. We know the spin state of a vector mass can be described by a 3x3 spin density matrix. And the diagonal element rho 0, 0 corresponds to the probability of finding a vector meson in space in spin state 0 out of 3 possible spin state, -1, 0, and 1. So if you see a deviation of rho 0, 0 from 1/3, that means you have a non-zero spin alignment. It could be it has a preference in the longitudinal mode or has a preference in the transverse mode. In practice, how do you measure it? It's very similar to lambda global polarization. So you take axis or as your quantization axis. In this case, we take the global angular momentum direction as our quantization axis. Then you trace, say, a phi-meson decays into K plus and K minus. Then you trace this daughter K plus angle. Its angle with respect to this quantization axis theta star. Then you feed it by this equation. Essentially, in practice, it's more complicated, but basically you feed that with this equation, you can derive this rho 0, 0. Rho 0, 0 equals to 1/3. That means in phi rest frame, the daughter K-on distribution is more like a ball shape. If it's greater than 1/3, that means it's like a standing peanut shape. And if it's smaller than 1/3, then it's a donut shape. So why we study vector global spin alignment? I already said there's no local cancellation when integrating over phase space as opposed to spin half particles. Spin half particles, so what you are probing is more sensitive to the order function, but global spin alignment is an even function. Then it has access to spin orbital force. This S times E. This is a strong force, electric field of the strong force field times the momentum. This term, it has a significant meaning in the nuclear shell structure. This term is responsible for producing this shell structure. But this term, you cannot get it, you cannot access it by studying the lambda polarization because it's canceled. Then the third reason is some mesons like phi are expected to originate predominantly from primordial production. So they have less decay contributions if compared to hyperons. They are more sensitive to early dynamics. Actually, STAR has measured the global spin alignment for phi and K star in 2008. This is a publication. This is a plot from the publication. The error bar is big because you see this is 0.2 to 0.3. Yeah, there's no conclusive statement. There's no significant result reported due to limited statistics at that time. Then in 2020, the Alice collaboration published the K star and phi-meson global spin alignment. So this is the K star. This one is the phi-meson. I would say, well, this is as a function PT. The right plus is a function of number of participants. I would say that the error bar is still kind of big. If you do the integral, the significance of deviating from 1/3 is on the order of 2 to 3 sigma level. But nevertheless, you see evidence of spin orbital angular momentum interaction. That's the conclusion from that paper. So you all already know at this quark matter, STAR released the results of phi and K star global spin alignment. This plot is plotted rho 0, 0 as a function of energy. The red stars are for phi and the cyan dots are for K star, neutral K star. You see for phi, you see you see some significant global spin alignment, while for K star, because the error bar is large, you can regard it for now is more or less consistent with 1/3. So that is a puzzle. It looks like a phi possesses surprisingly large global spin alignment, while K-star possesses little. Then how can we explain the large rho 00 of phi-meson? Since we released our preliminary results, it's about 4 or 5 years ago at one of the meetings in Stony Brook, I think. Over a dozen papers trying to explain the phi global spin alignment. Well, we can go over them one by one. So here I have a table list all the mechanisms that can produce global spin alignment. The first one is quark coalescence, and it has a vorticity and a magnetic field contribution, but the mechanism is cranked through quark coalescence. So here you have, if the contribution is actually from the magnetic part of the vorticity tensor, and this is the conventional magnet contribution. But these two contributions, they combine together, and this is constrained by the measured lambda global polarization. If you put that in, you will see that this contribution is on the order of 10 to the minus 5. And the 10 to the minus 5 on this plot is just like this dashed line. This dashed line is intended to draw the 1/3 line. And 10 to the minus 5 deviation from that, you will see no difference. It's just like a dashed line. So it's very, very small. Then this electrical component of vorticity tensor, it can also polarize the quarks, produce a global spin alignment. The calculation by 3+1D viscous hydrodynamic model gives a contribution of 10 to the minus 4. If you plot the 10 to the minus 4 on this plot, it still would be like this dashed line. So it's very, very small. The conventional electrical field, it can also polarize quarks, and people evaluate with the PHSD model with the magnetic field and if you do that with the peak, even with peak value from this PHSD model, you end up with 10 to the minus 5. That is again almost negligible. There's an early study showing that the fragmentation, if particles are produced by fragmentation, then the quark polarization will be carried over to produced hadrons. In that sense, they estimate that this contribution from fragmentation gives a contribution to global spin alignment on the order 10 to the minus 5. That's again very, very small. Recently, there are two works studied the local polarization. One is the helicity polarization, the helicity frame. Helicity frame, that means you have a polarization in the helicity frame. Helicity frame is you, instead of taking the global momentum, global angular momentum as the quantization axis, you take the quarks momentum as your axis. As your quantization axis, so that's the helicity frame. And if the quarks possesses a helicity frame polarization, it will reveal that effect on the global polarization as well, for the vector meson. Then there's another pattern. There's a circular, I call it circular polarization. That's a little bit more complicated. I will talk about it more later. But these two mechanisms, they both give a negative contribution. So they tend to produce a rho 00 less than 1/3. Recently, there's another work proposed by Ben Mueller and Dylan Yang. They look into this same mechanism that is responsible for local parity violation. If you have say, net excess of chiral charge locally, and that will generate some disturbance in the spin location. So you would have they argue a fluctuating actual charge current will produce some local spin preference will give some local spin preference, and that will also reflected in some way on the global spin alignment. From their estimation, they think that if this mechanism works, the rho 0 for neutral K star should be smaller than rho 0 of phi, and they both should be smaller than 1/3. So as you can see, none of those mechanisms I mentioned above, they can give they either give you a very small magnitude, or they give you a rho 0 contribution smaller than 1/3. And there's this recent paper work. This is led by Chun Wang, Shen Li Xin, and also I think Xin Liang also participated. In this, they argue that vector mass on strong field will produce a global spin alignment. This is the fit with this equation motivated by this theoretical work. This contribution is proportional to a quantity called GS, and then there's also inverse proportional to M score and the temperature score. And this GS is reflects this vector mass on strong force fields fluctuation. This B is just the magnetic component of the field tensor, and the E is the electrical component of the field tensor. So you do that field, you can even extract a quantity. So it's about a 5.7 amperes force. Oh, this denotes the fields, the strength of the field's fluctuation. I said about the vector mass on strong force field. So what is that force field? Before talking about that, I would like to remind us that the heavy ion collision environment is a highly volatile environment. Here you have a nucleus at rest, but if you have nucleus at relativistic energies, because of this Lorentz contraction, you will see a lot of non-planes, bumpiness, a lot of fluctuations. The bottom plot shows this fluctuation of energy from color glass condensate approach. But because that you have a lot of fluctuations, is a full fluctuation of quark and gluon fields, it will generate a local net quark current. In terms of strangeness, the net strangeness is still conserved, but locally you can have a net strangeness current. So that's where this effect is from. If you have a local net quark current, then like electrical charge in motion can generate a classical electromagnetic field. The S and S bar quarks in motion, they can generate an effective what is theorists call it the phi-meson field. And this phi-meson field, just like how the classical EM field polarized quarks and anti-quarks, this phi-meson field can polarize S and S bar quarks due to strong interaction. If you write down those contributions that I mentioned, that has a formula of a tensor expression. So here I have vorticity contribution, EM field contribution, and a strong force field contribution. You will find that their formulism is very similar to each other. Basically, they have two contributions. The first one is the magnetic part of the tensor contribution, and the second one is the electrical part of the tensor contribution. So the bottom one is a strong force field. Now I, in particular, highlight this part because this part you will not probe it with lambda polarization. My understanding for lambda, this part get canceled out. And again, this involves as a spin direction times this the global angular momentum direction. So that this term is responsible, well, if for the nuclear, is responsible for producing the nuclear shell structure. That describes the spin-orbital force. So it has a very interesting meaning. This idea actually was used to, this idea of phi-meson vector field was used to explain the difference in lambda and lambda bar polarization. But in that work, they study, the idea is, well, actually the idea of two papers are equivalent to each other, but the underlying mechanism are slightly different between the two. For the lambda global polarization in this work, what at work is the magnetic part of the meson field. And this is done by the magnetic interaction with lambda and anti-lambda. While for the phi global spin alignment in the previous work, I don't know that. Sorry. In this work, what at work is phi-meson field interacting with S quarks. So one interacting with the lambda particle itself, the other one is interacting with the quarks. But the underlying mechanisms are very similar to each other. Then the natural question to ask is, what about the K-star meson? Well, there's a follow-up paper that explains what happens to K-star meson. Basically, for phi-meson, because you have SS bar, they have the same flavor. The argument is that their field correlation is strong because they have the same flavor. But for K-star, you have a DS bar, and they have a different flavor, and they may point to different direction. Because what at the end, what matters is this term, the mean of polarization of anti-quarks times the mean of times the polarization of quarks. For SS bar, this term can survive, but the DS bar, this term may not survive. We don't know because it depends on how uncorrelated or correlated between the different flavor. Now then you would naturally ask the next question. So what about GSI? Because GSI has a similar configuration, right? So phi is SS bar. The next one is a CC bar. If this argument is right, you will expect that GSI also possesses a large global spin alignment. Well, first of all, we have to say for GSI, the kind of story probably will be a little bit more complicated because people usually argue for GSI, you have this screening effect. But nevertheless, let's look at the GSI. This is measured by Alice. This is shown at this quark matter. They use the lambda theta, but lambda theta is just relate to rho 00 by this equation. If the lambda theta is greater than 0, that means rho 00 is greater than 1/3. They indeed see a large, see that rho 00 is greater than 1/3. That's agree with this picture. However, they measured this GSI at the fault region. I don't know whether that make a difference or not. So, but anyway, this is what they measured. They do see deviating from 1/3 from the above. So that corroborates the idea of correlated strong force for QQ bar configuration. Well, the next one is the upsilon, VB bar. I don't know whether we can measure it. So maybe the CMS can give it a try. In the paper posted to arXiv, we also showed the centrality dependence. The top ones for phi, the bottom rows from K star. For different energies, you can see this interesting pattern again. At a larger energy, the signal tends to diminish, getting close to 1/3. What I would like to point out on this slide is, if you focus on the central collision, so here, you will see there's a tendency at a larger, in central collision, the rho 00 tends to go below 1/3. This is more obvious at the 200 J than at a lower energy. This could be due to the local spin alignment that I took in one of the previous slides. Here I borrow a slide from Mike Lisa at Quark Matter. Basically, the idea is you have two colliding nuclei, and then it will produce a two-ring structure, like here. And the matter will rotate from inside out, like was shown here, inside out along this ring structure. So you will have a ring of the vorticity field. And this vorticity field, one is clockwise, the other one is counterclockwise, depends on which side are in Z. This will produce a local polarization of quarks. And when you do the normal coalescence, it will reveal itself somewhere, some residual on the global spin alignment of meson. So this might explain what happens in central collisions. This plot, we show the rho 0, 0 as a function of transverse momentum for phi and for K star. Not shortly after we posted our results on the archive, the series come up with an explanation. Well, they have updated or in another sense advanced version of the theoretical framework to explain the phi global spin alignment. In this version, they generalized to describe phi-meson in motion, because the previous version they can only consider a static case, but here they can describe the momentum dependence. And this is their calculation. They only use two parameters, and they claim that they can explain most of the feature, which is indeed, I think, not bad, right? And this low energy compared to the low energy what I have, then you see how the higher energy becomes flattening out, and the magnitude becomes smaller. I think as a new mechanism, this is not a bad job at all. Although we understand there could be some associated uncertainty, but I think it catches the general feature of the data. They also explained the measurement of rho 0, 0 method in plane and out of plane. So what's in plane and out of plane? So usually what I've shown before is with the quantization axis as chosen as L, the global angular momentum direction. But you can also do that by rotating L by 90 degrees. So in that case, you take the reaction plane direction as your quantization axis. That's what we call in-plane rho 0, 0. And the data shows that out-of-plane rho 0, 0 is larger than that in-plane rho 0, 0. In the same framework, they can also explain this. I think the underlying reason for seeing the difference is because the elliptic flow. They have the similar rho 0, 0, but when you boost it into the lap frame, because you have more elliptic flow due to this due to this asymmetrical boost, you got the outer plane rho 0, 0 greater than in plane. But for the detail, you can maybe ask a Chun or Xinyan. At Quark Matter, we also showed the charge K star global spin alignment. So here is a K star plus minus. It has a quark content of, I think it's US bar. The neutral K star is DS bar. But again, for those cases which has a mixture of quark flavor, according to the theoretical work, it will be very hard to control. So the prediction will be very difficult. But nevertheless, we have this measurement, and we're waiting for theorists to interpret. And also we see this is for isobar. The measurement in isobar is for neutral K star is larger than in gold. We also studied a neutral K star global spin alignment between the K star and the anti-K star. There's no significant difference between them. And if you compare to that in measured in the previous, this is measured in isobar. If you compare that to measurement in gold, I would say gold is a little bit smaller, but considering R-bar, they more or less agree with each other, maybe within 2 sigma. So here's my summary. We have observed a surprisingly large global spin alignment for phi-meson. It cannot be explained by conventional mechanism. However, it can be accommodated by a model with strong force field. Another note I want to add here, also we are excited by this explanation, but like many other new explanation or new theory, it will take time for it to confront new challenges. So we are in this process, we'll see how it goes. For us, this is the first time we see that the strong force field is supported as a key mechanism that leads to global spin alignment. Again, this needs to be tested with more checks in the community, of course, from both the experimental side and the theory side. If this indeed turns out holds at the end, and this would be a potential new avenue for understanding strong interaction. In the future, I think it's desirable to expand the study for other vector mesons like GSI. Well, instead, we can measure GSI at mid rapidity, and the Wupsilon, I hope it is doable, and other mesons, D, B mesons. In 2023 and 2025 at STAR, we plan to take 10 times more statistics so that we have put our GSI global spin alignment at the mid rapidity within the RHIC. That will be good news. We will give it a try. Yeah, we wish for more theoretical development, and I know there's some debate on whether this mechanism is right or reasonable. I think that's a good thing, or I hope our measurement can stimulate more of such a discussion, and by this process we can learn. So I stop here.
Excellent. Thank you very much, Aihong, for a wonderful talk. We have time for questions. I'm going to ask a question quickly, which is, could you say, if when you study the J psi and the upsilon, if you see the exact same global spin alignment for the other vector mesons, what does that tell us?
This, to me, this would be give evidence to this explanation. So this argument that you for the configuration, while you have the same flavor, this SS bar and GSI CC bar and the Upsilon BB bar, because you have a strong correlation between the strong force field, this term will survive, and that is responsible for producing a larger global spin alignment.
Hmm.
But I heard that we also need to be careful in terms for GSI. That could be a screening effect. I don't know. So we have to see first and then think about it.
Okay, very good.
But at least for GSI, we already know at a forward rapidity, the Alice plot shows that is positive. So that's corroborated this explanation.
Yes. And then actually I have a super simple question back on slide number 7. When you were talking about the lambda baryon and saying that the strange quark is thought to carry all of the spin for the lambda hyperon, and that's because of you said because of the wave function, the isospin and the spin values of the wave function.
Right.
So the thing I don't know is, have we measured the isospin value for the lambda hyperon? Do we know that? It's isospin 0. I mean, do we know?
I cannot answer that question. I have to look back in the literatures whether that's the case or not. I cannot answer that question now.
Okay.
Maybe I'm not sure if somebody in the audience, the theorists, know this.
I wonder at the same time, is it possible to measure to find out if all of the spin is carried by the strange quark or not? Is that experimentally difficult to do?
That's a good question. I haven't thought about it.
Mm.
But this feature is purely from quantum mechanics. You have the plus, minus, then you write down this flavor spin wave function. You conclude that the spin is carried by the strange quarks. So this is in many textbooks, I think.
Oh, it was textbook. Okay, because I've used that before. I've written down that wave function before many times, but I wasn't sure if this was purely theoretical, strong theoretical grounds, or if it was also experimentally verified, the isospin value of the lambda.
I think, as far as I know, it has a strong theoretical ground, background, theoretical ground.
Yes.
Experimentally, I don't know. I cannot say because I haven't looked. I haven't paid attention.
Okay. Thank you very much.
Yeah.
And does anyone else have any questions for Aihong? Okay, if not, Aihong, I want to thank you from all of us again for an excellent talk. Thank you.
Thank you all.